Hello and welcome to our video on electrochemical gradients and cell membrane transport. My name is Aaron Calfolu. You'll hear from my partner Vicky Jagdeo soon. Our discussion will focus on the transport of sodium and potassium ions across the plasma membrane. This process has a dramatic impact on the animal cell's ability to induct and expel solutes. To understand why, let's first discuss electrochemical gradients. Electrochemical gradients consist of two components. First, the concentration gradient, and second, the membrane potential. Differences in solute concentration result in a solute concentration gradient. This generates a simple osmotic force directed from high concentration to low concentration. Differences in ion concentration inside and outside the cell result in an electrical driving force directed from positive charge to negative charge. By adding the contributions of membrane potential and concentration gradient together, we arrive at the net driving force, which is the electrochemical gradient. For sodium ions, the two components of the electrochemical gradient work in the same direction. Outside the cell, we see a higher concentration of sodium ions than on the inside, leading to an inward concentration gradient. Generally, cells have a negative resting membrane potential. This means that the positively charged sodium ions, moving from positive to negative electrical potential, have an inward electrical driving force. So we see that they add together and move in the same direction. For potassium ions, the components of the electrochemical gradient work in opposite directions. Now we see a higher concentration of potassium ions inside the cell than on the outside, leading to an outward concentration gradient. We again have a positively charged ion that will tend to move into the negative electrical potential within the cell, so we have an inward electrical driving force for potassium ions. This means that in the overall electrochemical gradient, we have forces moving in opposite directions. I'll now turn it over to my partner Vicky, who will discuss some of the ramifications of this in terms of cell membrane transport.
As my partner Aaron said, I will be going more in depth with the sodium and potassium pump and how concentration and electrochemical gradient come into play with it. Going back to the previous slides, we can see that the sodium and potassium electrochemical gradients work so that potassium has an outward concentration gradient and sodium has an inward concentration gradient. Moving solutes with the electrochemical gradient can be done passively without energy input, but going against the electrochemical gradient requires an energy source. For example, an ATP pump must be used to drive sodium against its electrochemical gradient, pumping it out of the cell. Passive gradient-driven pumps can be used to bring sodium into the cell, as I have stated before in this slide. ATP is used for this transport of sodium. The influx of sodium provides energy for other ions to be transported against their electrochemical gradients. This process uses 30% of the cell's total ATP consumption and plays a key role in the energy consumption and usage of animal cells. Specifically for the sodium and potassium movement, the sodium pump expels it from the membrane so that sodium concentration inside the cell is lower than outside. The vice versa occurs for potassium. There is a steep concentration gradient of sodium across the plasma membrane. This steep concentration gradient has a lot of energy stored. It acts together with the membrane potential to move sodium into the cell. The energy is used down the concentration gradient to move sodium. It is also used to actively transport potassium up the gradient and out of the cell. This coupled pump of sodium and potassium combines the membrane potential and concentration gradients of both ions to actively transport both ions across the plasma membrane. Thank you, and we hope that you learned a lot about the sodium and potassium pump.